In our class today, what we'll do is look at the graph of y equals root x, or the square root function, as I like to call it. So before we head into this one here, let's just review the gallery so far. And when I talk about the gallery, I'll talk about the gallery of basics. So this graph here is the y equals x linear. This one here is the y equals x squared parabola. This here is the y equals x cubed cubic. This one here is the y equals 1 on x hyperbola, asymptote there and there. And in the last lesson, we looked at this one here. It's the y equals 1 on x squared truncus. Okay, so these are our basic. So today we'll put the new entry into the gallery. It's the y equals root x or square root function graph. So what is the square root of 4? Okay, if you think the answer is plus or minus 2, read on. Many students think that it is the case, but it's simply not true. So the year 7 teacher was right. Okay, the square root of 4 is equal to 2. Okay, so how do we know when it's going to be negative? Well, if I want the negative root of 4, I have to actually ask for it. So notice that that negative sign there implies that what you're going to do is take the negative root of 4, which the answer is negative 2. Without any sign next to it, it's implied that the answer is going to be positive. Some of you will think, but you said that it's going to be plus or minus when you root. And yeah, I did. So here's the case that I want you to refer to. So just say we're trying to solve this equation here. What I need to be aware of is that x squared is equal to 4 when I solve it. I'm asking for the values that will make this true. So what I would do is take the root of both sides in this case. So x squared gets rooted, okay, and the 4 gets rooted as well. So plus or minus the square root of 4, which is x is equal to plus or minus 2. Now, why plus or minus? Well, remember, positive 2 goes in. Positive 2 when squared is equal to 4. So that's true. And negative 2 when all squared is equal to 4 as well. So there's two solutions to this problem. Whereas these ones here are just numbers being operated on. So this is 4 being rooted. We want the positive root of 4, which is 2, the negative root of 4, which is negative 2. So generally the plus or minus will come up when you're solving and you're taking the root of both sides. These, the root has already been taken or being taken, and they're telling you it's the positive root. All right, now the rule y equals root x, or x to the power of a half, because remember that second rooting a function is the same as raising it to the power of a half, corresponds to the graph to the right. That's that graph there. So why is there a domain restriction on the graph? Like, why isn't it the set of all real numbers? Well, let's explore the root x function by popping in some values. X is equal to 0, y is equal to the square root of 0, and when I square root nothing, I get nothing. So 0, 0 is a point on the function. Let's pop 1 in. X is equal to 0, y is equal to root 1, square root of 1 is just 1, so y is equal to 1. 1, 1 is a point. There it is right there. X is equal to 4, let's pop 4 in. So y equals the square root of 4, and that's 2, okay? And that's that point there. So that's the point when x equals 4, y is equal to 2. I could bang values in between, but they'll all work out to be irrational values. Okay, but what it does is it increases from 1 and 2, but all of these values in between here will be irrational. Okay, so if I pop 3 in, that I get root 3 out. Okay, so an irrational number. Why then can't I put negative numbers in? Well, the best thing you can do is actually try it out. So x is equal to negative 1. So I want to shove negative 1 in and see what happens. So I get y equals the square root of negative 1. And you might be thinking, well, what's the problem with that? Well, my challenge to you is find a number that when is multiplied by itself ends up to be negative 1. And the answer is that you can't. Because if you choose a negative value, let's just say you say, oh, isn't it negative 1? Well, negative 1 times negative 1 equals 1. Is it 1? 1 times 1 equals 1. And the fact of the matter is that a negative multiplied by a negative is a positive, and a positive multiplied by a positive is a positive. So you're never going to be able to make a negative number when multiplying a number by itself. It'll always be positive. Okay. Now let's see what the calculator says when I ask it to do this. So shift and hat will give you this square root template, -1, and it says, hey, that's not real in calc. Okay, so we say y equals root -1 is not real. Now, why does it not give you an error? Well, here's an interesting take on the problem. What I'll do is go out of the real number system and go into a different number system. It's called the complex number system. And in the complex number system, I can square root a negative number. I can square root -1, and I get an imaginary number. So what mathematicians did was they developed this imaginary number to pretend that this did exist, and then further engaged in the complex number system. Okay, so that's what they do in specialist maths. We here in methods are the ultimate applied mathematicians, and we just say that is not real or can't be done in applied maths. Okay, so what we can do is transform the root function in exactly the same way that we transformed every one of these graphs here, okay? So this h and k will translate it left or right. This a value will dilate it from the x-axis, and if the a value is negative, it'll be a reflection in the x-axis. So we simply read them off exactly the same way as we've done so far. So the graph of y equals root x undergoes the following transformations in the order given. So first of all, it gets dilated by a factor of 2 from the x-axis. So it's going to become y equals 2 root x. And that's that transformation. Now let's reflect it in the x-axis. That's y equals -2 root x. Translated 1 unit to the right. So what happens is this x value here has take 1 added to it. Remembering that, what that will do is actually move it 1 unit to the right. Just like a parabola, y equals x take 1 squared plus 2. You would tell me that the turning point of this is 1, 2. That same thing applies to the root function. And the translation 3 units up will be a +3 on the end. Okay, and there's all our transformations done. All right, so find the new equation. So that's it there. And sketch the resulting graph. Label the axes intercepts with coordinates. State the domain and range. Okay, so draw up your Cartesian planes in your notes, please, girls. And what we'll do is we'll note that this is a translation 1 unit to the right and 3 units up. So when we're translating, what we can do is we can translate any point, but what the best point to move is this point here. I call it, and this is my word, not the proper maths word, but this is my word. I call this the anchor of, and I call this the flick. All right. So this is the anchor of the flick. So what will happen is the anchor of the flick moves 1 to the right and 3 up. So I'm going to go 1 to the right, and here's 3 up. There's the anchor of the flick. Now what happens is it gets reflected in the x-axis. So instead of flicking up like this, so remember the basic will go like that, moved up and there, and then what will happen is it gets reflected. So it's going to go down. So it sort of flicks down like this. So I can see that the x-axis intercept is going to be somewhere there. I can also see that there's not going to be a y-axis intercept. Okay, that's just not going to happen for us. All right. So what we'll do is we'll get the x-axis intercept, which occurs when y is equal to 0. So 0 equals -2 x take 1 plus 3. Then we're going to subtract 3 and divide by 2, which will give us 3 on 2 equals root x take 1. Now we're going to square both sides. 9 on 4 equals x take 4 on 4. Now I'm going to add 4 on 4 to 9 on 4. X is equal to 13 on 4, or x is equal to 3 1/4. So here's 1, here's 2, here's 3, and a little bit further over is 3 1/4. Okay, label the flick. Okay, again, remember that's my word, not like a technical word. So if mum or dad's a maths professor, don't be going around talking about the flick on the root function. They won't know what the hell you're talking about, and they'll wonder what on earth I'm teaching you. All right, so there it is there. Hey, just say you were adamant, Mr. Miller, I want to find the y-intercept. I want to find it. Even though you're telling me that it doesn't exist, I'm going to go find it. And that's fantastic. Do it. Okay, so remember that the y-int occurs when x is equal to 0. All right, so here goes. Y equals -2. Now I'm going to pop 0 in there, and I've got 0 take 1. Oops. That's not allowed. Okay, that's not real in the number system that we operate in, the real number system. So what the maths is telling you here is, hey, that y-intercept that you're trying to find, it doesn't exist. Okay, so you got to listen to the maths. It's trying to kick back and it's trying to tell you, hey, whoa, it doesn't exist. Stop right now. All right, now we need the domain and range. The domain is the set of x values that you can pop into this function. Now remember, the original domain for the root function was x is an element from 0 to infinity, and because this graph moves 1 over, that will change. So the lowest value you can pop in is 1, and the largest value you can pop in is positive infinity, i.e. it'll just root anything above 1 inclusive. Y is an element. What can come out of the function? So we basically start down and look up, and we can see that it can go from -infinity all the way up to and including, and it can pump out a 3 at the anchor point. Okay, sketch the graph of this, stating the domain and range of the graph. Okay, so I can see quickly, we've got a translation 1 to the left and 6 units down. So I'm going to take care of that part first. Okay, so 1 to the left, -1, and 6 down, and here is my anchor point. Right, now this 3 is a dilation factor 3 from the x-axis. We're not really worried about that, other than to say the basic one looks like this. If it gets moved down and down like this, it's going to result in something like that, which means that this is going to give us an x-intercept and a y-intercept. So let's get the y-intercept first. Y int. You don't need to write this, but I like to put it into my notes. Y int when x is equal to 0. So that's going to be y equals, so 0 goes in, we get the square root of 1, which is 1. 3 times 1 is 3. 3 takes 6 is -3. So the y-intercept rather is 0, -3. So there it is there. Okay, so it's going to go through, and it should be 2 or 3 or something like that. So x int when y is equal to 0, 0 equals 3 root x plus 1, take 6, add 6, divide by 3 is 2, square both sides, and I've got 4 equals x plus 1, x is equal to 3. So when x is equal to 3, y is equal to 0. So 1, 2, 3, round about there. Not bad. 0, -3, and 3, 0. Probably want an x and a y label there. State the domain and range. Okay, so the domain is a set of all x values that you're allowed to put in. So what we're going to do is start at -1 here. So it'll start producing y values at -1, and you can keep throwing x values in to positive infinity. Y is an element, so the lowest value it will pump out is -6 itself, and then it will keep producing values all the way to positive infinity. Okay, the rule y equals root -x for x less than or equal to 0 yields a graph which is a reflection of the graph of y equals root x in the y-axis. Right, so this graph here I'm going to suggest to you is the y equals root x function reflected in the y-axis. All right, interesting. So what many students tell me though is they have a problem with this. And the problem they have is they say, you said you can't square root a negative number. And I always say, yeah, I did say that. So we're going to say that like something like the root of -4 does not exist. Okay, so I stand by that. I absolutely stand by that. So students look at that and they go, but what about that? That's a negative number. And I go, well, not necessarily. Not necessarily. For the values of x larger than 0, it will be negative. Try 1 and you'll note that that's -1. Try 2 and that's -2. But what about the negative values for x? If you pump in a negative value, for example, -4, what we'll do is we'll note, so we'll say x is equal to -4 and we'll put it in. That means that we get -4, or -4 is negated to equal 4. So y equals the square root of 4, which is equal to 2. Okay, so what it basically does is instead of only accepting positive values, this negative sign allows us to accept the negative values and actually ignores the positive values. So it feels like that's fair. That's fair. That's a good way of giving these negative values of x some action. All right. So knowing that we can flick in this direction here will help us sketch this graph here. Now, my very strong suggestion to you girls is that you rewrite this graph as this, i.e. what we would do here is go, okay, this is y equals root, and then we take -1 out as a common factor, and we say that this is x take 2 plus 3. All right, so -x plus 2. All right, so that's a different way of looking at it. Okay, it's the same rule, just looks different. Now, why do we want to do this? Well, once we've got it into this form, girls, what it allows us to do is read off the transformations. So I know that this 2 here sends the graph 2 to the right, and I know that this 3 sends it 3 down. So I'm going to put that in to my sketch so far. Okay, so 2 across and 3 up. So there's 2 and there's 3. So there's my anchor point. All right, now we're used to flicking that way for the root function, but this negative sign here means that these values get negated, which means that this function actually is going to flick in this direction. But you can actually test it out as well. So if you're wondering what way to flick, pop in a value higher than 2 on this side and see whether it works. So let's just try the value 3. 3 take away 2 is equal to 1. 1 gets negated to be -1, and we're trying to square root -1, which we can't do. Okay, so that means that this direction here is not true. We don't flick this way. We've got to flick this way here. All right, and I'll try 0, which will be the y-intercept. So let's go and sub x equals 0 to find y-int, the y-intercept. So y equals, so 0 goes in, we get -2. -2 gets negated to become 2. We've got √2 plus 3. Now, √2 is roughly 1.4. 3 plus 1.4 is roughly 4.4. So here's 1, 2, 3, here's 4. Round about here would be where it is. So that's going to be 0, √2 plus 3, and the anchor point is 2, 3. All right, what about an x-intercept? Okay, is there an x-intercept? Well, you can see here that there isn't, but what happens is something very, very interesting. So what we'll do is we'll get an x-intercept. So I'm going to get an x-intercept which occurs when y is equal to 0. So I'm going to say that -3 equals root negative x take 2. Right, so all I've done there is I've subtracted 3 from both sides. Right, now what I'm going to do is square both sides, and I get 9 equals negative x take 2. So now I'm going to divide both sides by -1. -9 equals x take 2, x equals -7. So what it suggests is that actually this does have an x-intercept, okay, and it actually occurs down here, -7. Right, and this is a little tricky to explain, but what happens is sometimes when you square both sides to undo a root sign, what you do is you introduce what's called an extraneous solution. Right? So what we've done by squaring both sides is we've introduced a solution that was otherwise vetted beforehand. Okay. So the moral of the story is algebraically, it suggests that there is an x-intercept. But if this is our function, we can see that it's not going to work. And again, you can try it out by putting -7 as a value in. So if I put -7 in, I get -9. -9 gets negated to be 9. Square root of 9 is 3. 3 plus 3 is equal to 6. So when x is equal to -7, the y value is 6 and not 0 as well, as this suggests. Okay. So again, the moral of the story, know what you're looking for in an answer or a solution, what it's going to look like. So if the algebra suggests otherwise, you kind of go, yeah, but I know that's not going to be the case, or I know that that might be an extraneous solution, okay? But again, here to note, the extraneous solution was introduced when I squared the root and squared this side. What it does is it brings in to play a solution that was vetted out beforehand when it was probably attempted to square when we attempted to square root it.